topic 4 for exponentials is specifically about growth and decay, which we've talked about growth and decay throughout this unit already, just because that is often what exponentials are shown as. It's just something that's growing or something that's decaying. But just to make sure that we understand what that means, growth is when something is increasing exponentially, just like when you grow, your height is increasing. And decay is when something is decreasing. Usually, again, we're talking about like a population that is decaying, or like bacteria decays, it gets smaller. So the formulas that we're about to write in this box are used when the growth or decay rate is given as a percentage. That is really the most important thing that I'm going to say about topic 4 is percentages. If you see anything that's given to you as a percentage, you have to use these special formulas. They're still derived from our same y equals a times b to the x. We just have to kind of adjust this b to reflect that percentage. So exponential growth is y equals a, parentheses, 1 plus r to the t. And exponential decay is almost exactly the same, except it's 1 minus r raised to the t. That's an r, sorry. This is where my board goes wonky. That's an r. So, again, it's very similar. It's just that instead of b, we have that 1 plus r part, okay? This might also look familiar because it's very similar to compound interest that you did in 7th grade. The a, just like it was down here, stands for our initial amount. So it's still the y-intercept. It's the initial starting point. The r is the percentage rate, okay? But you do need to change it into a decimal in order to work with it. And then the t is time in years. Okay, so again, anytime you're given a percentage and you say that something is exponentially growing at a rate of 12% or whatever, you need to make sure you use 1 plus that rate or 1 minus that rate, depending on the problem. So, number 1, we're just going to jump right in. The population of a city is increasing at a rate of 4% each year. In 2000, there were 236,000 people in the city. Write an exponential growth function to model this situation and then find the population in 2009. So, using that formula, A is first, it's the initial amount, which in this case is going to be that 26,000 number, 236,000, sorry. Then we do our parentheses, 1. We have to decide is it plus or minus based on if it's increasing or decreasing. So in this case, it's plus. And then the percentage. So in this case, it's 4%. I need to move that decimal 2 times. So right now it's 4 with a hidden decimal after it. So if I move it 2 times, it'll be 0.04 raised to the time. Well, in this case, if they're wanting to know about 2009, that's 9 years later if they're giving us 2000 as the starting point. So I'm going to type in my calculator 236,000 times 1.04 raised to the 9th power. So I should find my answer just by typing that in. Make sure you use a little caret to type in your 9. And you should get 335,901.5877. Now, the reason I didn't write that down is because we're talking about people. We're talking about the city population. So we could sit here and debate all day long about whether or not we should round up or round down. But technically, we only have 335,901 whole people in this city at this point. 0.5877 is not a whole person yet, so we're not going to count them. However, some people would say, well, rounding rules says the 0.5 means we round up. I'll tell you that most of the time, either the answer rounded down or rounded up will be accepted. So this is fine, or 335,902, either way. Okay, that's all that was. So let's do the right-hand side. Now we have a population that is decreasing. So there's 35,000 people in 2000, and it's decreasing at a rate of 6%, so 0.06. They want to know what will the population be in 2012. So that's 12 years later. So I've got 0.94 raised to the 12th. All I did there was take 1 minus 0.06 and actually subtract 0.06 from 1. You can actually type this top one into your calculator. It's smart enough to work that out. But if you want to simplify it a little bit, you can actually go ahead and do the subtraction. I will say I've seen the STAR test sometimes do the subtraction already and have you pick like which equation makes sense. So we type that in and we get 16,657, again 0.21102, but again, that's not a whole person, so you can stop it here, or if you want to round up, that's fine too, either way. Okay? So, moving right along, we're just going to practice it. We only have 3 more problems, and this topic is literally done. It'll be a quick one. So, it says the number of sports radio stations has increased. There's our clue that it's going to be growth at an average of 14.3% per year. if there were 220 sports radio stations in 1998, approximately how many should there be in 2013? So our initial starting point is that 220. It's increasing, so I'm going to do 1 plus. Move this decimal 2 times, so 0.143. And we're talking about a span of from 1998 to 2013. That's a span of 15 years. So I'm going to put a 15 up there. Again, all that's left to do is type this in your calculator. And we get 1633. Again, rounding up, rounding down, it does not matter, it's up to you. Okay, I'm going to go ahead and pause my screen and let you try the next one on your own. Number 5 is actually a little bit different. We'll talk about that one here in a second, but try number 4 on your own. Alrighty, so you should get 1,084, again, 0.7 something, which you can round up or down depending on how you want to do it. But make sure that you did subtract that 0.02 because this is a decreasing problem. It's an exponential decay problem. So number 5, this is kind of a random problem that was just thrown into this topic because this topic was already so short. But this is a table of an exponential graph that we are going to try to create an equation for. Topic 2 was all about writing equations. We know it's a times b to the x, where a is the initial value and b is the rate. But looking at this table, I don't have the initial value. It would be somewhere in here. And it's also kind of hard to find the rate, not only because it's decimals, but because of these numbers. They're jumping all over the place, right? The only place that has a jump of +1 would be here. So I need to really focus my efforts on these two numbers and try to figure out how do I go from 15.625 to 78.125. Well, if you can't see it, you can always just divide it in your calculator. I'm going to divide that 78 number by the 15 number, and I get 5. So now I know this was just times 5. Okay? If I want to know if that really works, well, this is technically 2 jumps of times 5 times 5. So I could try that here. I could multiply 0.625 by 5 twice and see if I get this. And you will. So now I know that the b is a 5. So part of my problem is done. But I still need my initial value, which is usually found at the 0. Well, if I know that the 1 is 0.625, to get back to 0, I would just divide 0.625 by 5. And I get 0.125. Okay, so again, that was just kind of thrown on there, a random little problem, just to talk you through some of the problem solving you might have to do with exponentials. You might have to do a lot of working backwards to find initial values. You might have to do some division to find out what was being multiplied in the first place. But when in doubt, use your calculator to help you out. That would be our equation for that one. In general, exponential growth and decay is not a big deal as long as you remember that a percentage has to be changed into a decimal. So if you have any questions, please come ask me.